All right, let's jump right into today's explainer. We're finally bridging the gap between those theoretical electrical concepts we've talked about and the actual physical nameplate hardware you'd see out on a modern offshore drilling rig. Up until now, we've treated variable speed drives, or VSDs, as these generic black boxes that just magically make these massive rigs function. But today, we're tearing down that abstraction. We're going to look at the exact vendor equipment portfolios and the component engineering that power these multi-million-dollar operations.
Here's our roadmap for today. We'll cover theory meets reality, the water-cooled workhorse, air-cooled multi-drive, direct torque control, specifying the drive, and finally, powering the motors. Let's get to it. Section 1. Theory meets reality. It's time to put some real names to those generic concepts. So the core job of a variable speed drive on a rig is pretty straightforward, right? It drives massive drilling motors, rotary tables, top drives, mud pumps, you name it. But doing that same exact job requires totally different physical architectures depending on the environment. We're looking at two very different cabinets that tackle this exact same problem in their own unique ways. And wow, this really highlights the contrast. On the left, you've got the ABB ACS 600W. This beast literally drinks water to stay cool. Then on the right, the ACS 800 multi-drive breathes air, and thanks to some pretty incredible internal processing, thinks for itself thousands of times a second. 2 drives, 1 job, totally specialized engineering DNA. Moving to Section 2, the water-cooled workhorse. Let's zoom in on that water-cooled system first to see what makes it tick. This is the ACS 600W, and as you can see, it's a totally enclosed, rugged marine cabinet. When you're out there in the highly corrosive, just brutally unpredictable environment of a drill ship or a jackup rig, you really can't always rely on ambient air for cooling. So this drive rejects its heat through a safely sealed freshwater or seawater cooling loop. By keeping the electronics completely isolated from the outside atmosphere, it guarantees a safe, silent operation no matter how bad conditions get outside. And here's the crazy part. That sealed system doesn't sacrifice any muscle, not even a little. This family spans from 400 kilowatts all the way up to an absolutely massive 4,300 kilowatts. To put that into perspective for you, that's almost 5,800 horsepower. You're basically running a modern diesel locomotive inside a sealed box on a drill ship. As long as you've got the cooling water loop architecture in place, this single product line can scale to run virtually any major piece of machinery on the vessel. Section 3. Air-cooled multi-drive. Okay, so what if you don't use water cooling? Well, before we look at the alternative cabinet, we need to quickly recap the architecture. Remember single versus multi-drive topologies? A single drive means every single frequency converter has its own diode supply unit, its own inverter, and its own feed from the switchgear. But with a multi-drive topology, you use one common diode supply unit to feed several independent inverters, all hooked up to a common DC bus. This is a total game changer. It means a way more compact footprint, fewer components, less cabling, and you can even share braking resources across several drives. And this brings us to the actual hardware. This is the ACS 800 air-cooled multi-drive. It's exactly that shared DC bus architecture we just talked about, productized into a highly compact, premium air-cooled design. You get a ton of output from a really small footprint, all while sharing a common user interface and control platform. Section 4. Direct torque control. Now, the physical layout is cool, but the real magic of the ACS 800 is in its digital brain. You'll see this gold label on these drives, DTC, which stands for Direct Torque Control. And I need to stress this right now. Do not mistake this for just some marketing fluff. This is a fundamental, real-world shift in motor control engineering that completely changes how these rigs operate. Let's break down what DTC actually does. Older variable speed drives, they control a motor indirectly by regulating voltage and frequency. You're basically telling the motor what speed to go and just hoping the torque follows smoothly. But direct torque control actually measures and controls the motor's torque and flux directly in real time. It recalculates these values roughly every 25 microseconds. I mean, that is lightning fast, vastly faster than the blink of an eye. Because it's not relying on a slow, conventional loop, it responds to load changes almost instantly. This gives you exact, hyper-precise torque control right down to zero speed. Imagine a massive drawworks hoisting thousands of feet of heavy drill pipe. The ability to hold full torque, accurately, at zero speed without slipping, that's not just a nice-to-have. That is an absolute safety and performance necessity. Section 5. Specifying the drive. All right, so we've got the theory and the hardware. Let's do a quick reality check. If you're a commissioning engineer or a rig designer faced with a blank single-line diagram, which of these two families do you actually choose? Which one directly maps to the multi-drive topology, and which one fits a closed-loop system?
Well, it comes down to a pretty clear decision matrix based on your cooling setup and your electrical topology. If your vessel is committed to a water cooling loop, which is super common on drill ships or tight machinery spaces, and you need massive power, the ACS600W is your go-to. On the flip side, if your design leans into the multi-drive topology to save on cabling, and you want air cooling combined with that insane 25 microsecond precision of direct torque control, then the ACS800 multi-drive is exactly what goes into your spec.
Section 6. Powering the motors.
Of course, the drives themselves don't do the actual drilling. Let's move to the other end of those electrical cables and look at the physical motors doing the mechanical heavy lifting. This right here is where all that highly controlled electrical power turns into raw, punishing mechanical force. These rugged AC drilling motors take an absolute beating, massive vibration, crazy shock loads, extreme environments. Today, enclosed AC motors have largely replaced older DC ones because there are no exposed brushes or commutators to maintain. They're just fundamentally tougher.
Take a look at this portfolio data. You can see how different frame sizes and pull speeds cover everything a rig needs. For instance, the HXR 450 LM8 pumps out 820 kilowatts at 950 RPM. That is plenty of continuous power for a heavy mud pump or a large drawworks. Then you have something like the HXR 400 LK6, delivering 560 kilowatts at roughly the same RPM. It gives engineers total flexibility depending on the exact load requirements of the rotary table or cement pumps.
But hey, it's vital to remember that specs go way beyond just kilowatts and RPM. Look at the AMA series here, specifically the AMA 423 M6. Sure, it steps up to 950 kilowatts, but it carries a mechanical spec that is absolutely critical, a radial force tolerance of up to 120 kilonewtons. That means the shaft and bearings can take a massive amount of sideways lateral load without failing prematurely. Matching that kind of mechanical robustness to the electrical output is exactly how you make sure a rig doesn't break down during a critical drilling phase.
Which brings us to our final thought. Over the course of this explainer, we've replaced generic black boxes with real, tangible product lines. You know the difference between marine water-cooled drives and air-cooled multi-drives, and you've seen the heavy-duty motors they control. So here's my challenge for you. On your next real-world commissioning project, can you mentally trace that power flow? Can you picture it moving from the raw diesel generators through the shared DC bus of an ACS800, being calculated every 25 microseconds by direct torque control, all the way down to a 120 kilonewton tolerant motor shaft, turning a drill bit miles beneath the ocean? Synthesizing that entire chain, that's what separates the theory from true engineering expertise. Keep learning, keep focusing, and I'll catch you in the next explainer.